Let's follow a message, not abstractly, concretely. You're sitting at your laptop. You open your browser, type a URL, and hit enter. That action produces data, packets, small chunks of information, each labeled with where it came from and where it needs to go, released into a network that will carry them to their destination. Where do they go? How do they get there? Who, or what, makes the decisions? This is the question this entire series has been building toward. Not what is routing in the abstract, but what actually happens, step by step, to a real packet, making a real journey across the real internet. Every concept we've covered, routing tables, route selection, how routes are discovered, what convergence means, what can go wrong, all of it shows up in this one journey. Let's trace it. Your packet starts on your local network. Your laptop produces it, a request to load a web page, addressed to the IP address of a server somewhere on the internet. Before the packet can go anywhere, your laptop needs to get it off your local network and onto the wider internet. It sends the packet to the first router it knows about, your home router or your office gateway. The first hop, your home router, is a small, simple device. It has a routing table with almost nothing in it, a handful of entries for your local network's devices, and one entry that covers everything else, the default route. The default route points to your ISP. For every packet destined for the internet, which is nearly every packet that leaves your home, the home router's decision is the same: send it to the ISP. No complex computation, no multiple paths to evaluate. Just one door, and everything goes through it. This is route selection at its simplest. The routing table is tiny, the decision is trivial. And that's by design. Home routers don't need to know how to reach every corner of the internet themselves. They just need to know where to hand off packets to someone who does. Your packet crosses into your ISP's network. Now it's in a different world. Your ISP operates a network that might span a city, a region, or an entire country. They have dozens or hundreds of routers, all running dynamic routing protocols, sharing information with each other about what's reachable through which paths, continuously updating their routing tables as the network changes. When your packet arrives at your ISP's first router, that router has a much richer routing table than your home router did. It knows about routes within the ISP's own network. It knows about routes to other ISPs they've connected to. It knows about routes to major internet exchanges, physical locations where networks meet and exchange traffic. The router looks at your packet's destination address and performs a longest prefix match lookup, finding the most specific entry in its table that covers that destination. Maybe it has a specific route for the destination network. Maybe it falls back to a less specific route pointing toward a transit provider. Either way, it makes a decision in microseconds and forwards the packet to the next hop. Notice what's happening here. Nobody planned this specific packet's journey in advance. No central system looked at your request and mapped out a route. The router made a local decision, the best next hop given what it currently knows, and the packet moved one step closer to its destination. The next router will make its own local decision, and the next ons, each one contributing one hop to a journey that none of them see in its entirety. This is the distributed, decentralized nature of internet routing made visible. The intelligence isn't in any single place. It's distributed across thousands of devices, each doing a small piece of the work. At some point, your packet likely passes through a major internet exchange, one of the physical facilities where different networks connect to each other and hand off traffic. Internet exchanges are extraordinary places. Enormous buildings filled with networking hardware, where cables from hundreds of different organizations, ISPs, content providers, cloud companies, universities, all terminate in the same switching infrastructure. The whole point is that traffic can pass between any two connected networks efficiently, without having to transit through multiple intermediaries. The routing that makes internet exchanges work is BGP, the Border Gateway Protocol we covered in the hijacking video. Every organization connected to an exchange runs BGP with the others, announcing their address ranges, learning each other's routes, making policy decisions about which paths to prefer and which to avoid. Your packet, moving through this exchange, is the product of dozens of BGP policy decisions made by organizations you've never heard of. Your ISP prefers certain routes for cost reasons. The network on the other side prefers certain paths for performance reasons. The exchange itself has peering agreements that govern whose traffic can flow where. None of this is visible to you. It's all encoded in routing tables, expressed as BGP policies, operating silently underneath your connection. This is also where the risks we discussed become real. The BGP system your packet is traversing is built on trust, each network accepting the other's route announcements without cryptographic verification. Most of those announcements are legitimate, but as we saw with Pakistan Telecom and YouTube, a single illegitimate announcement can redirect traffic in ways nobody intended. And BGP's speed of propagation means the impact spreads globally in minutes. Your packet's journey depends on that trust holding. Now your packet is getting closer to its destination. It's been handed off from your ISP to an exchange, from the exchange to another network, from that network closer to wherever the destination server lives. At each hop, the same process, arrive at a router, longest prefix match lookup, forwarding decision, move to the next hop. The routing table consulted at each step was built through dynamic routing protocols, routers sharing topology information, computing shortest paths, propagating updates when the network changes. But here's something worth pausing on. The routing table your packet's journey depends on right now reflects the network state as it was when each entry was last updated, not as it is at this exact microsecond as it was. Routing tables are always, to some small degree, a picture of the recent past rather than the present. Under normal conditions, this doesn't matter. The network changes slowly enough that the picture is accurate enough, but you've now seen what happens when it isn't. When a link fails faster than convergence can spread the news, when a route flaps and the table oscillates between states, when a misconfiguration causes routes to disappear entirely. Each of those failure modes is a case where the routing table your packet is relying on contains information that doesn't quite match reality. The internet doesn't guarantee your packet will arrive. It makes a best effort, forwarding each packet based on the best available information at each hop. Most of the time, it works. When it doesn't, the failures we've discussed in this series are what you get. Your packet arrives at the destination network. The server that hosts the web page you requested sits inside this network. The last few routers in the journey are handling traffic within this network, routing to the specific server that will respond to your request. The server receives your packet, processes it, generates a response, the data for the web page you requested. That response gets packaged into packets of its own, each addressed back to you and released into the network. Those response packets make their own journey, possibly through the same routers your request traveled through, possibly through different ones. Routing is not necessarily symmetric. The path from A to B and the path from B to A can be completely different. Eventually, the response packets reach your home network. Your router delivers them to your laptop. Your browser assembles the packets into the web page. It loads. The whole journey, your request out, the response back, took somewhere between 20 and 200 milliseconds. During that window, your packets pass through somewhere between 10 and 30 individual routers. Each one made a local decision. Each decision was based on a routing table built from dynamic protocol exchanges with neighbors. Each table reflects a network state shaped by convergence events, route advertisements, and BGP policy decisions. Let's zoom out one final time and see the whole picture. Your home router handled the first hop with a trivial routing table and a single default route. Your ISP's routers used dynamic routing inside their network and BGP to exchange routes with neighboring networks. Major exchange points let traffic move efficiently between networks. Every router along the path made local forwarding decisions using the longest prefix match rule. Underneath all of it, the routing tables. Each one a model of the network, as that router currently understands it, updated continuously as the network changes. Never perfectly current, but accurate enough most of the time. And around all of it, the failure modes, convergence windows, loops, flapping, hijacks, cascading failures. Each one a consequence of how distributed systems handle imperfect knowledge. The internet works because thousands of independently operated networks share routing information using common protocols. No central controller, no master routing table, no single organization that knows the full path between any 2 points. Just routers. talking to neighboring routers, building tables from what they learn, making local decisions that in aggregate route your packets across a planet. That is routing. Not a single mechanism, but a family of mechanisms working together all the time underneath every connection you make. Invisible when it works. Dramatic when it doesn't. Fundamental to everything the modern internet does. Your message was delivered. Now you know how.